Okay, we start up again. The problem with the central space scheme, unconditionally unstable. He explodes no matter what you do. So now, first order upwind scheme for this one. And the recipe then exactly as before, but now also including time. So you have this one, and the derivatives now based on a positive velocity, of course, saying a0, and here uij, ui minus 1j over one single delta x. And the last one, j minus 1 over one single delta y equal to 0. There you have it. First order upwind. Let's see if that one helps, because this one, he goes berserk. So I will comment out these two. Well, we can copy them first. Then we comment them out. So now let's make upwind scheme. So the recipe here said the new one equals the old one minus C temp. Now I guess I don't need that half anymore, and my temp is somewhat different. I don't have I plus 1 like that, and I don't have j plus 1. That's the only difference, isn't it? So now this one should be the four unknowns here. Let's try that one. First order upwind. It doesn't explode, but he disappears. I mean, the solution for the problem is not like this. The initial disturbance should only be moved. It should be advected with a constant velocity. It shouldn't be distorted like this. Maybe a remedy here is actually to use bigger time step. I had a very small one, 0.01, so let's multiply him with 10. He's still running down here. Bigger time step. No, that was a very bad idea. How big time step can I use? The Courant number, as you can see down here, I printed out. Courant number is 1. Shouldn't that be allowed? What's the stability criteria? What's the stability criteria? Isolate the new one, and then everything else on the other side. What do we have? Let's see, delta t up, you will have lots of these delta t a0 by h, being delta x or delta y, they're the same. So when we rewrite it now, the new one equals the old one, n, and I have one here, and then I have another one here, and another one there. They will be negative on the other side, so I'll have minus 2 times the Courant number for these guys. These two, being negative here, will be positive on the other side, so they will be both multiplied with the Courant number, ui minus 1j, and ij minus 1. There you have the stencil. The sum of the coefficient, 1 minus 2c plus c plus c is 1. Very nice. Then next demand, all coefficients positive. Then this one will demand your Courant number must be 1/2. Let's see if that is true. Courant number 1/2. Then I need a time step of that was a little bit too much, 0.5 I think. Let's see if that's correct. Yeah, now I have a Courant number of 0.5. I should be just on the limit. Let's see if that one is stable. Well, more or less. It looks a little bit shaky. So I think it was a little bit too much. But we can check it now. Go a little bit higher and see. Oh yeah, that doesn't look good. Clearly unstable there. So we need to keep it more smooth, you need a smaller one actually. To be on the stability limit here is not a good idea. So now you see he's quite smooth. Courant number is below 0.5 and it looks okay. But this smearing out effect, the diffusion effect is still present clearly. If you want to move him another direction, you just flip the signs here on some of these, and actually it's very easy for this one if I recall correctly. Switch that one to +1 instead. Then he will move in another direction. Any questions to this one? That's okay. The diffusion is there. It's present when you choose the upwind scheme. As you saw last time with the modified equation, it can be shown again. A little bit more work. But clearly, yes, it is diffusive. Now it's possible, if you throw away most of what you have learned so far, and think a little bit differently. It's a transport of any signal u with a constant velocity a0, which means the new velocity in a single point should be based on what? Well, it should be based on whatever is left for you and down. So if you do something crude like that, skipping here everything with delta t and Courant number and everything. Now let's see what happens. So this is the initial state, and then he moves just perfectly. So why do we need so very, very complex? You can even make him go in another direction, of course you can. You just switch the numbers here if you like. What did we use here instead? +1. Of course we can make this guy move around in the direction that we want without him being distorted. Yes, we can do that. Now actually what we're doing is solving a totally different equation system. So sort of an hyperbolic solution technique. You rewrite your original equation to be oriented alongside the characteristic lines, and then he will turn out to be an ordinary differential equation, which then can be solved. So this we can say is an interesting phenomena, but it doesn't really help us. Remember, in the end, we are going to have several terms on the other side here anyway. Pressure, diffusion, gravity, whatever, for the entire Navier-Stokes. So the hyperbolic direction, interesting, but no remedy for us in the end. Finally, I wanted to show you, let's see, where was the old one? Should be here somewhere. Back to this, the previous demonstration of the wave equation. Here, now with the Dirichlet conditions. So we have a project student. He's working now with surface waves, and he's going to investigate the surface wave from boats, from ships. And what he is then interested in is not all this noise here. He's going to be interested in, say, the initial situation, and then he will sort of only look at the first waves going out from a boat. But sadly for him, I mean, he has to limit himself. He has to just simulate a part of the ocean. He's going to need some boundary conditions, and he's going to need some boundary conditions that does not reflect waves. How can you do that? No reflection. No reflection. So the waves, they should just go out and disappear, shouldn't come back. You could use a Neumann condition instead of Dirichlet, but that doesn't help. The wave will still come back. So what should he do? Well, we sort of got the idea when we had this problem, and we looked at these advection equations here. Here you have it perfectly. It just goes out and disappears. That's exactly what he needs. But this is not a wave equation. So how to combine this? Just wanted to show you. This is what we have done so far. So this is sort of the same problem that we had with the ordinary wave equation. But you see the red rectangle here. The inner domain, that is the wave equation. This boundary zone here actually is quite big, 10 cells at least. Here I programmed the advection equation. So it's a mix. And I mean, are we allowed to do that? Well, why not? There's no law against it. Physically, it can be really hard to understand. But you see the effect, not perfect. You get a little bit reflections, but most of it just disappear. So yes, you can sort of think outside the box here. We have one domain, one piece of space where we solve one equation, and here all of a sudden we jump to something else. Why not? Why not? If I zoom in a little bit, you can see it's not entirely perfect. Zoom in for the boundary zone a factor 10. A little jumpy at first. But then you see clearly it's not a perfect drain of the wave. And the reason here, the problem, is the Courant numbers for the two different equations. To get the advection equation to sort of be perfect, then you demand Courant number of 1. Then he will sort of solve it following the characteristic curves. But that would meaning pushing too big delta t on the wave equation. Then he will be unstable, because he has a requirement that the Courant number must be smaller than square root of 2.5. So the stability limit didn't match. That's why we get sort of not a perfect drain of the wave through the boundaries. But it's not that many percentage left, so I think it's yeah, at least an option for him. Anyway, it's not my problem or yours, it's his problem. But I mean, we have a task like that for a project and master, yeah, absolutely. Okay, we still have time left. Any questions from you guys? I mean, the MATLAB programming, I assume, goes okay. I haven't heard anything else from the assistants, so you are beginning to getting skilled in MATLAB programming, which is good. Okay, next time we will focus on a little bit simpler system, one-dimensional waves, but then it's going to be compressible flow, and then peaking towards the say the Euler equation, one-dimensional gas equations, a little bit more messy. Then you need continuity and momentum to solve it. But that will be next time. I think I'll then stop here, and then we continue next time.